Okay, so we said that we have this function that we can use to describe the system, which is the Hamiltonian, which is essentially the total energy of the system. And then we have these equations, basically, that allows us to reconstruct the equation of motion, Newton's equation. But also, I'm saying that now we can already see that this is a first order in time equation in time, and there is the energy involved. So the energy enforces the dynamic of the system completely, which should give us a bit more confidence. The fact that the Schrödinger equation as well is something interesting because it's the first order derivative in time, and then there is this Hamiltonian here that plays a role, and then there is your function that you want to solve for. And we know that we can start to work with the easy solution. The easy solution is the free moving object, so just kinetic energy. Suppose you have a mass which is moving at a certain speed in space, and we want to know what the solution of this motion is. We know what it is in classical mechanics. It's a straight line, so we know the coordinate will follow a straight line, and there is not, we can solve that easily. Let's see what happens in quantum mechanics. But before doing that, we need to give sense of what is P and in quantum mechanics, in this operator here, okay, the Hamiltonian. And to do that, we need to do a step back and remember that in quantum mechanics we are dealing with matrices or operators, let's say, on complex functions. But and one thing that you need to remember also is that there is something called uncertain Heisenberg uncertainty principle. Certainty principle that says that when you measure x, you have an uncertainty, so some delta x minus x0. So delta x. So you have or x1 minus x0. So the difference between two values. So you are not certain about the value. So you have some uncertainty. It's actually a statistical measure of your variance of your distribution. But anyway, it doesn't matter. So you don't know what the value is exactly, but you can measure it. And then you multiply by the same amount for momentum. And momentum, we know that is mass times velocity is equal to momentum. This is the definition. It's the almost amount of energy that is in the system, except that is a vector. And this must be greater than a value that we know, Planck's constant, a squared over 2, for example, something like that. And this tells us that you cannot measure precisely position and momentum at the same time. And also, this is completely related to the fact that the operators that represent x and p have this property that mean that they are not commuting. Non-commuting. And this is obviously false in classical mechanics, because in classical mechanics, if you put any two numbers, position and momentum, which is on the straight line, you can find them in the straight line, it would be always 0, because a times b minus b times a is always 0 with numbers. With matrices is not the case, because you can find easily matrices. There are plenty of matrices that are maybe the majority that do not follow this rule, that they are not they do not commute. For example, pick these two matrices, very simple, and you will get 0, 0, 1, minus 1, 0. But if you do the other way around, 0, 1, 1, 0, and then you get 1, 0, 0, minus 1, you swap the minus. meaning that this A times B is different from B times A, where A and B are these 2 meters. Yeah, so we need just to find the same set of relationship between two operators, okay? And the easiest thing that you can think of when you work with functions are two things. So you can multiply a function by its position. Suppose you have a function and you have f of x. You can call the operator x acting on the function the multiplication of f of x on the point of x. You can do that. It's very easy. It's a very simple operation that you can do on function. And then you can call another easy one that you can do is f of x is derivative of x in x. Derivative. Okay. Now let's not call it p because this is not exactly p. Let's call it another p naught. There is some constant that we need to play with, but what I want to make it the momentum. But to give you an example of why this is working is that if you do x derivative of x of a function, and then you do derivative of x of a function, those two things are different. And the difference, because basically this side here leads to f of x times x f prime, and this is f prime x. F prime is the derivative. And we can see that the difference is exactly f, meaning that we are looking at something of this case here where we swap x and p and we apply it to f, we get something that is proportional to f. So summarizing is that we are quite lucky, because if we consider two simple functions, a simple operation on function like the multiplication and the derivative, we already have two examples of operators that can be used to describe the physics of the uncertainty principle, because structurally they behave the same. So we can argue that this is a good starting point, and in fact it turns out that it is. And by doing this we can actually plug it into the Schrödinger equation and basically solve, and then we get minus derivative square 2 m, because there is the momentum, x squared times psi. Okay, and this is it basically, because we have that the solution, we can prove that the solution of this equation, which there is an I, is e to the I px minus t p square over 2m psi of x and t. And then next time I will show you why this is few fact about this and why this is a solution. But we can prove it easily, because we can derive it twice basically. Yeah, if you derive, yeah, we can show it super easily, and then I will close this video. But let's see that this is the solution, and then we will discuss about the solution. I will give you just few comments about this solution. But the solution that is, so the equation is IH dt psi minus 1 over 2m derivative second x squared psi. And I claim that the solution is psi t, a function of time, t. Okay, This is a complex number, as you can see, so we know exactly what a complex number is. Is some complex number with modulus 1, so it's the probability, the square of it is 1, meaning that the probability is 1, which makes sense. So modulus of x and t is equal to 1, which is fine, meaning that we're not doing something wrong. So everything, all the possibility that can happen will happen. So this is what this is saying. But then we do derivative over time of this equation, and we multiply by h bar, and this is exactly, if we derive time, we get I p square over m, yes, and then we multiply by h and I over psi, because yes, because we know the derivative of an exponential is, we know that, right, is that exponential with a constant value up front. So we can see that the derivative over time is here. There is a constant value in front of time, which is the same constant as a, which drops down, and we get the same function here. And this is basically the idea that the exponential, when you differentiate the exponential, you get a x, and this is the idea. We did it already in the video on exponentials, and we can see that this is the part that we're dealing with in time here. Now, if we do the derivative of x twice, it's the same thing, but we just deal with this part here because the time is a constant, so we'll not differentiate the constant, and therefore we get plus square, so we get that derivative square over of our function is equal to minus times minus is minus t square of the function. And this is good because if we multiply by h and divide it by 2m, we get that these two parts are exactly the same. We get that this part is exactly the same as this part here, and this part here is exactly, and these one are exactly what we have here in our equation, the two sides, a and b. This is a and this is b. Okay, so what I just want to say is that this this formula here, which I write here again, TP square, which is a complex number, as you can see, the evolution of which is the modulus of which is 1, meaning that the total probability of this particle to be somewhere is 1, as we know, and it behaves like this. Okay, so suppose the initial position. So this is basically yeah, this is the prototypus of our function, and then next time we will discuss the part where the Hamiltonian is 1 over 2m p square plus kx square, the other part square, which is the potential energy of the spring attached to the system, which is not a free moving object, but we need to be a bit more analysis. And also I will give you the connection between the position and the momentum. So this is the solution of your free falling object, but sorry, what I will give you is an idea of why delta x over delta p is greater than h squared over 2. And with this function we we will be able to see it quite clearly using Fourier transform. So I will try to do two things to next time. Maybe discuss a little bit about the uncertainty principle with the Fourier transform using this solution here, and adding the extra bit of physics in the harmonic oscillator and the equation. So I hope you liked this video. I hope you enjoyed it, and then let's see where we go next with the future ones. See you next time. Bye.